Hello, this is a video regarding Unit 4, Chemical Trends and Bonding. We are still in Chapter 7, and we will be talking about ending the last, or the third trend that is talked in Chapter 7, and continue on and talk about some of the overlying trends of the three major groups of the periodic table. Let us begin. So, electron affinity, as we have seen, is tied to the atomic radius that our elements have. So, by definition, it's the energy needed to that comes with adding an electron to the uh, actual molecule. And from that, again, some of this is again going to be all tied into that trend that we had talked about earlier, and that is atomic radius. Atomic radius, as we've said, is the biggest one to pay attention to. So everything after that has a kind of a conceptual connection to the size of the actual atom, or its natural neutral atom part of it. So we're going to now be looking at the addition of an electron as opposed to ionization energy that we have talked about previously, which was the removal of an electron. Usually, like I said, the electron affinity would be exothermic. It would as you go from left to right. So as we go from left to right, it becomes more energetic or exothermic, and as we can see, the values increase as we go from left to right. And again, they're negative because they're giving off energy, just as a reminder on that. There are some, again, oddities, as that would make sense. It wouldn't be chemistry without some exceptions to the rules, so to speak. And again, some of that comes from our understanding of how the electrons are placed in their orbits or orbitals, if you will, as we move forward with it. But we see that overall trend, and that as the atomic radius is getting smaller, it takes more energy is released when that is when that actually happens. Now, these would also be more, what we would guess would be more thermochemically acceptable, because they want to almost have those electrons there because they're just one short of their octet. These would usually will gain 2, gain 3, and again, there are weird group 14 or 4A group tends to just kind of they're kind of in that middle road where they're not really sure what to do, where were they going to go with that. We have that there now. The explanation, like we said, we'll talk about that in the next slide, about why there's this odd thing and then why there's this odd thing that happens as well. So the first one, as we said, occurs when you're going to go from at first groups from 2A, 1A to 2A, because adding too many electrons, as you would already have, is going to increase to that p orbital. And when we look at, say, what that looks like, and what that looks like is kind of, again, going from like a 1s2, to add something else, we would have to go to a 2s and then add something there. So there's going to be some energy needed. But if we had our fill of it, and we already had, say, like lithium, where 1s had its fill, and then its 2s was going to go there. If we were going to add 1 to it, that's going to happen, then that can happen there. But why all of a sudden does beryllium I'll go a little bit of a different way is because to get more electrons into what this would be beryllium would require us to add the 2p electron or orbitals there to put that additional electron there. And so that's where you kind of see where that happens. Now, when we look at the other ones, why does it go for different for like kind of going from 5 kind of there? Why is there discontinuity between 4 and 5? Is because at 5, when we have our 2p, and we're going to look at, say, nitrogen, when we have that filled in, that's what the electron configuration for nitrogen would look like. To add another M1 there, it's got to go into one of these spots here. And to do that, that requires kind of like a forced entry. Kind of like, I've used the analogy before that, sharing a room is an enjoyable experience. You're going to resist having to share a room with them. Well, that's because the electrons, again, negative charge, opposites attract, like charges repel, and because the electrons are repelling each other, that in itself kind of like forces that, no, please don't come in here. I already have my own space. And then now all of a sudden it's like, well, now I guess we're sharing. So those other electrons are going to start taking them on as well, just to kind of like, okay, guess we're sharing. Here we go, moving on forward with it. So it is again, an energetic thing. It's a paying attention to the why comes back into the where do I have to add another orbital that, technically it's probably there, but it's not being utilized all that much. And then to actually access it it requires a little bit more for that. And then to, again, add an electron requires more the kind of that repulsion, and it's not as thermochemically acceptable. Now to kind of give us some general overview of the groups on the periodic table. And we've always kind of utilized that there are 3 main groups on our periodic table. Metals, non-metals, and metalloids. We mentioned this in chapter 2 when we had discussed naming. Now we kind of just give them these brief overviews, and these brief overviews are nothing that's probably actually surprising at this point in time in our learning, in that metals usually the one that makes the most sense for students is that metals are good conductors of heat and electricity. That's why we use copper wiring for electricity, even though silver is the best. Gold is kind of like second best, but it's the quan that kind of requires that. It's a little bit more money. Heat. That's why we use metal pans. Copper is common. Aluminum is kind of common. The feng shui thing is to use more of a cast iron as well. And so there becomes a little bit of the why do we use that? Well, they good conductors of heat and electricity, and we've known about that for quite some time. They are bright, metallic, and luster, kind of give us that bling bling. For us, that's why we use gold and silver and platinum and a lot of these other metals in here, trick out our vehicles with their chrome, so that it has that shiny luster. You wouldn't do it if it didn't have some look to it. That's why the bling bling is such an important part. The fact that they are malleable and ductile does allow them for artistic purposes, and actually in some cases jewelry and other means as well. And in the fact that they can be drawn into wire, hammered into sheets for war purposes would include that as well. But they are, as we can see and as we've seen from our naming, this was the vast majority of them. They are all solids at room temperature, as we would probably, hopefully, come to guess. Most of us know about mercury being the one lone liquid on the periodic table. As I've mentioned before, there are two liquids on the periodic table, mercury being one of them. We'll talk about the other one in just a little bit. Metals tend to have low ionization energies. When we were looking at our trends on our periodic table, they tend to lose those electrons very easily. That's because, again, their atomic radius is so much bigger, and therefore that losing those outside electrons is very easy for them. It also becomes more, the why they lose again is, again, looking at that octet rule. But those are the things that we see why they have those low ionization energies. That also, in turn, also makes them very good at producing that electricity. That one electron, those two electrons hanging on that outside, allows for that transfer, that flow of electricity to actually happen. A lot more investigation on that would be looked at in electrochemistry, which is a much later chapter, usually seen in the second semester of a general chemistry class. Many of this became a large amount of our naming because they are usually there. The metal oxides are an important one, so it would be kind of like a copper oxide is kind of why is the Statue of Liberty green? It's because of the metal oxide that the copper oxide that forms. That is actually what it was intended to look like, that green color on the outside. That's why an artist that utilizes copper in their art is going under the impression that at some point it is going to age with time and it is actually going to form that. That's why a lot of our houses actually have a copper tubing in them for plumbing purposes, so that it actually forms this nice little layer on the inside, actually protecting the copper from a lot of wear and tear, such as like an iron oxide would not do that, as an iron oxide, more likely commonly referred to as rust, that many of us see on our cars in this area. We're going to see that there, and that's why they're very abundant, they're common, and it's a lot of that iron oxide sometimes that we also see on why we need to have salt that has a red out, so to speak, name in our salt water or water softeners, and so that's kind of why that one becomes a thing. There are many other metal oxides that are there as well. They also tend to be basic, not just simple. Basic meaning having a pH greater than 7. When we talked about kind of our acid-base chemistry, they would kind of tend to form those that are considered to be bases by definition that we had looked at once prior. The nonmetals, well, they're not metals, and they are a small group on the periodic table. Majority of them are gases, as that the noble gases are all. You have carbon, nitrogen, oxygen, fluorine, chlorine tend to be the gases, with a few other sporadic other ones. They are poor conductors of heat and electricity. Well, that's also because they're not gases, or they're not metals, I'm sorry. You would also see that hydrogen is also a gas over there. Always forget about that one over there. And so then it's kind of a thing. Typically they're not really all that fun to look at when they are in their natural form. Phosphorus, sulfur is just a yellow powder. Phosphorus has a couple different versions of it. Iodine is just kind of a purpley color, and so it kind of just, they're not really fun to look at. I mean, carbon, the only thing that carbon does is when it is in its allotrope, and we see that diamond, but of the other allotropes of carbon, are very dull in nature, and it is only that very specific diamond allotrope of carbon that makes that one look nice, and a little bling bling action going on with that. They're not malleable or ductile, even when they're in their solid form. They can be pressed into pellets, though, but they kind of, and that's why we see them as kind of the early forms to use when we are looking at pill making as well. And so those are always a part of that process. They're small group on the periodic table, not the smallest group, but definitely a lot smaller than that of the metals. As we have discussed before, that there are seven of them exist as diatomics. That means that they exist in a double form, such as, again, as we've looked at before, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They all form in that diatomic, meaning when they're in their natural stable state, that's what it is. We also have bromine as our other liquid that we have on the periodic table, and iodine is our solid of that group. And so we do have a little bit of both going on there. And if you really look and pay attention, our group 17 represented is that we have a gas, and then we have, again, a liquid and a solid. And so as you go down the periodic table, you actually get all three states of matter in group 17. As we've kind of looked at and discussed, that group 17 behaves a lot, has a lot of similarities to how they behave, and that comes down to kind of the why in looking at their electron configuration. As we've mentioned before, the noble gases, well, they're gases, and that should come at no surprise why they are. They don't interact under normal conditions. They can be looked at under other, they can go under chemical reactions under other means, but it usually takes a lot of heat and pressure to kind of get them to react and force them on to do that. They tend to be the anions, as we've looked at when our naming. Where did all the non-metals, we kind of identified them for our naming purposes back in chapter 2. And so that's where this kind of brings it back in, and they because they form anions, which again forms that negative charge. And so they tend to form and react with metals, which forms the cation, which is a positive charge. And look, there's an electrostatic attraction, and therefore we get that. Typically, they tend to gain electrons again, forming that anion. And a lot of it is to fill that lower gas, that outer shell, so that they have their electron configuration. That octet rule comes into play. When we looked at acids back in earlier chapters, we said that these will also tend to form what are known as acidics or acids, and so that becomes again the why. Well, they are a proton donor, so to speak, and so that begins that process of kind of the why those things work. Our last group is the semi-metals or metalloids. These ones tend to be named as we looked at in chapter 2, similar to the non-metals with the monodi stuff. These ones tend to form some very important compounds that we see, such as a silicon dioxide. Very pure silicon dioxide can be used in semiconductors. They tend to have properties of both metals and non-metals because they're kind of in that in-between group. And if you look at a pure agate of silicon, it will be very much look very shiny and metallic in nature. Not like silicon that you would put it for like caulking. around the house. That's a completely different thing, but it has silicon in it, but it's a little bit different with that. For me, it's always interesting to see that how the metalloids have changed over time. Back in my day, you had to walk to school and uphill both ways. Not really, but aluminum when I was in a junior was a metalloid or considered to be a metalloid, and it's upon further investigation that some of those metallic properties are kind of came out, and that we now look at and view aluminum as a metal and not a metalloid. There are that will probably change for a couple of these as well. That they kind of go with that. My kind of hard and fast rule is that if it touches kind of the staircase, chances are you would be correct in almost saying that it is. There are two of them that don't, and that's kind of where you get those little variations in it. Semiconductors, because they don't are kind of what they really are known for. And that's mainly because they don't conduct electricity all that well, but they do conduct electricity. And so we want to make sure that they are kind of utilize that and they get their moment in the sun when we talk about the kind of the groups of the periodic table as we see here. That will conclude our video for today. I'll hope to see you back again.